this morning, I'm meant to talk about prebiotic chemistry in the solar system. So it's a big challenge considering that it's a 1.5-hour slot. So I won't be able to cover everything for sure. And some of you might be a bit frustrated because I make some large editorial cuts in order to try to cover in depth. I'll try to go in depth in some of the aspects, and some other aspects will be certainly left over. But well, that's the rule of the game. So the idea is to think about how, from what we know about the prebiotic chemistry on Earth, and you've heard about it extensively yesterday already. I will try to build a little bit on what we heard yesterday to think if there is any possibility to have such processes occurring elsewhere in the solar system. So starting from simple compounds, physico-chemical conditions and reactivity of those compounds to get into more complex structures, even more complex and organized, and maybe life. So I have to do editorial cuts. I'll focus a lot on the small bodies. So there's not really, prebiotic chemistry occurring on the small bodies, but it's one of the reservoirs of the ingredients that can feed, all the planets of the solar system to bring some ingredients. And what is convenient with the small bodies of the solar system is that, we have samples in the lab, meteorites. We have been lucky enough to have space probes to go to some of them, to study them, to make an inventory of their content. And then I'll get into other objects of the solar system. Jorge Vago will talk about Mars tomorrow, so there's a lot to say about Mars. So Mars suffered a lot of editorial cuts, but you will get more about Mars tomorrow, and I'll try to spend some time on the icy moons of the giant planets, which are now in the, on the spotlight, under the spotlight of the space program, the press, the media attention. I'll try to address that. So I said there's a lot to say. But if you just look at some news you get on the press, it looks like the question is already settled. Methane on Mars, does it mean Curiosity rover has found life? It was on The Guardian in December 2014. Here in Scientific America, NASA rover finds mysterious methane emission on Mars. Is there life on Mars? As soon as there's something weird, something that is not well understood, one of the basic answers you will immediately get, that will get a lot of attention, not necessarily by scientists, but by the press and the public, is that life could be the answer. And we'll talk a little bit about Mars, and I'll try to talk about this methane question. That, yes, why do we think it could be life, and why are we attracted by this answer? And more recently, it was earlier this year. It's the attention, as I said, the spotlight turned to the icy moons. Here, it was an observation of plumes that were ejected from the Saturn moon Enceladus, and plumes from Saturn moons hint that it could support life. So there are icy particles that are ejected from this small moon. Well, one of the best understanding we have from this moon is that there might be liquid water. There have been analyses of the composition of those icy particles showing that there is organic matter. There are traces of hydrogen and various compounds that hints towards the fact that there might be hydrothermal activities at the bottom of the liquid ocean of this moon. So liquid water, organic, hydrothermal activity, energy, well, life, and life almost for sure. I mean, it looks like it's taken for granted that as soon as you have this combination, this magical combination of liquid water, organic material and energy, you would be able to find life. Here it's food on Enceladus. There is energy, there is organic material, so there's food. There's food for the life that sometimes it's written is, and people might understand is that might, but we have no idea. So it was a preliminary introduction, and these are the main outlooks of my presentation this morning. So I will come back quickly on those ingredients, what they are, what people pay attention to, and what we are actually looking for. And I'm part of it. I'm not saying I know everything, no, I'm part of this community wondering about whether life could arise beyond Earth. So I will come back about that, and then, yes, I will focus on the composition of the small bodies of the solar system, because they are a source of organic material, so what we find in these primitive bodies, so organics off the shelf that are delivered to planets, and I'll get to Mars icy satellites more quickly, certainly, and then back to the recipe, back to the ingredients to put it into a larger context. So the ingredients. So as I said, the traditional way to consider the origin of life is to have this trinity: water, chemistry, organic chemistry, and energy. So this is one of the web page from the NASA Europa Exploration Program, and basically it starts with that. Do we have the ingredients for life on Europa? And you have this list with 3 items. And well, do we even know they are the ingredients of life? Because as far as we know, life exists on Earth, that's for sure. We have some ideas, some theories about how it occurs, but we don't have the complete view. We are not, nobody yet has a final answer about how life can arise somewhere. But it's taken somehow sometimes for granted, and this is the life ingredient list. So does it, if you have this combination, does it mean you get 100%, you have 100% chances to get life, half, 50%, 1%, one out of millions? We have no idea. We don't know if it's well. It's not. It's sometimes it looks like it's a chemical reaction, while we don't know. So it's more, for me, it's more an axiom. It's a way. It's useful to have axiom. It's useful to have a theory, but an axiom is or postulate is a statement that is so evident or well established that it is accepted without controversy or question. But we don't know. It's accepted. We think it's it makes sense to consider that this combination could lead to the apparition of life, but well, no one ever demonstrated that. So it's a postulate. So what are we looking for? So really, Pareto yesterday told you about this this idea that life is something that is able to make copies of itself and evolve. So I like this definition from André Braque. Life is based on little robots making copies of themselves and capable of evolution. Evolution meaning mistakes at some point. It makes a mistake. The copy is not the same, exactly the same that it was before. And in some context, its mistake will be good. It's depending on the environment. It would benefit to this new to this new copy, or it would be something that is not good, and it won't be kept. So that's the basic idea. We are looking for something that has the capability of self-replication, autocatalysis, and evolution. So if you show it in a different way, you've seen some of this scheme yesterday. So you start with C, so that will be our starting compound that will react with R, and the first step will be to have an intermediate. And if you want to be able to evolve, to have this cycle, you need to make sure that the reverse reaction is negligible. If you want it to loop like this, you don't want to have an equilibrium at the first stage. And it comes with an energetic cost. So you can't have anything looping like that at whatever energetic conditions. There have been studies about that showing that if you want this to be able to turn around, to self-replicate, to auto-replicate, it needs to have an energetic cost at the first stage. So you get there, you get to the intermediate, but you need to make sure that this reaction back to the starting point is not easy. So it has energetic and kinetic implication. And then when you are in the intermediate, you get another C, and you can use the one C to make another C, and again and again and again. So this is an autocatalytic process. And from time to time, one of the C will be transformed into another compound called C prime. It's a mistake in the replication, and in a given environment, this mistake can be favorable for the auto-replication of C prime versus C. It's a kinetic. It's a kinetic question, and then you will have your loop, and with C prime and not C as in the beginning. So that's actually what we are looking for, and I'll come back to that later. It keep this energy cost in mind. So we now go to the second part, prebiotic chemistry in the solar system. As I said, I will focus a lot on the small bodies and review what we know about some class of meteorites, carbonaceous chondrites, what we know from comets, the composition of comets, and I will discuss and highlight some of the Rosetta results, the Rosetta mission results, and how all this stuff can get there. It's an important question. It's not saying, oh, we don't. Sometimes we say it's hard to understand why such or such compounds could be synthesized in the primitive Earth, depending on the hypothesis you put on the environment of the primitive Earth. But, well, it's not, the idea is not to push this question back and say, okay, it's on the meteorite and comet, and we don't mind why they get there. We have some idea about that. And we will talk a little bit about Mars and icy moon. So carbonaceous chondrites, it's our first step. So there are many kinds of meteorites. So meteorites are rocks that you can collect on the ground. So if it's in space, it's an asteroid, it's a comet. But yes, to be a meteorite, it's something that you find on the ground, on Earth, on Mars, or anywhere. But it's something that you can analyze, take back to the laboratory, and some of the meteorites are known to be rich in carbonaceous matter. Here you have a picture of the Murchison meteorite. Here it's a picture of a fragment of the Murchison meteorite. Here is a picture of a fragment of the Orgueil meteorite. And there is an ongoing flux of such objects on Earth, roughly 10 tons a year of meteorites, but much more of micrometeorites. Well, the estimations are not easy to make, but you can say that a lower limit would be 10,000 tons of micrometeorites a year. So a few percent of the meteorites are carbonaceous chondrites. And in those carbonaceous chondrites, up to 3% in mass is made of carbonaceous matter. So it's not much, it's a few percent. We call them carbonaceous chondrite, but it's not a piece of carbon. It's mostly rocky material, but part of it, a small part of it, is made of carbon. And Murchison meteorite is like the rock star of the carbonaceous chondrite, because it fell in the late 60s in Australia, in the desert, so in a very dry environment. It was observed. It has been collected right away, so it didn't stay on the ground under the rain for days, months, or years, like some other meteorites. It's been collected right away. So, and it's been collected in a controlled environment to prevent contamination from Earth material. So in this meteorite, we have been able to detect more than 75 amino acids. Amino acids are the building blocks of proteins. Among those amino acids, 8 are actual amino acids that are used by the living system on Earth. So it's a tiny amount, but they are here. And if you want a distribution of the soluble part, I'll go back later about soluble, insoluble. But if you analyze the soluble fraction that you can extract of meteorite like Murchison meteorite, you will have this kind of distribution of organic matter. It's dominated by carboxylic acids, but you also have a lot of other kind of chemical families, among them amino acids, among them alcohols, amide, heterocycles. So a lot of organics that some of them are considered to be quite reactive and can be involved in synthesis of more complex structure. So this is the same but with more details. So amino acids attract a lot of attention because it's quite simple to say proteins are made of amino acids. Life requires protein, and so if you have amino acids, you just add them one to another and you get the protein. That's far from being that easy. As you've heard yesterday, there's a lot of ideas pointing to the fact that maybe a structure like RNA came first before protein, so maybe paying that much attention to amino acids is not really relevant, because maybe you don't need amino acids to build life, but that's not sure. And the other thing is that as soon as you have amino acids, and we'll see that's quite easy, it's not that complicated to synthesize amino acid. The tricky part is to put them together and make small chains of amino acids, which we call peptides. And I'm not talking about proteins, which are huge chains of amino acid. But one thing is attracting the attention is that amino acids, I forgot to put one slide here, but amino acids can exist under two forms, two geometry. For one formula, one name of amino acids, you can get what we call chemists two configurations. They have the same 2D structure, but when you put them in 3 dimensions, they exist into two forms. Like your hand, you have the palm, 5 fingers. It's a formula of your 2 hands, but you won't be able to. They have image in a mirror, but you won't be able to. They're not the same. To pass from one end to another, you have to cut some fingers and rearrange. So that's the same thing with 2 configurations of amino acids. And in Murchison meteorites and other carbonaceous meteorites, it has been found that some amino acids exist with an excess of one configuration compared to another. It's what we call the L configuration. So let's say the left hand, it's the orientation, it's action towards polarized light, but I won't get into those details. So there is already a small excess, but for some of them it's up to 15%, so it's not negligible, of some excess of one configuration compared to another. And it turns out that life, to build protein, is using only one configuration, and it's the L configuration that is used by life. So, and it's a big question how what we call homochirality was selected and was implemented into the first living being on Earth. And if there is a small excess that is already brought from space, maybe that was a small push towards this selection compared to another. At least it's self-consistent, but we don't know. So maybe amino acids are important after all. And the latest results obtained on carbonaceous chondrites are quite impressive. Now we are using the most sensitive techniques, high-resolution mass spectrometry. And this paper that was already published in 2010, they analyze again Murchison matter, and they demonstrate that they were able to see a chemical diversity of tens of thousands of molecular composition. So tens of thousands of formula. But when you have a formula, let's say C5N6H12, you can combine them in different manners. So these techniques only says we have this formula, this formula, this formula, this formula. And then when you expand all the combination you can have with one formula, you get to the conclusion that there are likely millions of different organic structures that are present in small amount, but that are present in the Murchison meteorite. And this is one of the figure of this paper of 2010. So yes, the idea of high resolution mass spectroscopy is based on the fact that what you learned in before, if you're not doing high-resolution mass spectroscopy, you don't pay attention to that. But so you learn that H is 1, C is 12, N is 14, oxygen is 16, and well, you can live with that. But it's not entirely true. C is 12 by definition. So it's 12, O, because it's a mole of material is defined to match this requirement. But hydrogen is not 1, it's 10078, and nitrogen is not 14, it's 14003, and you can read oxygen is a little bit below 16. So then you can make a lot, you can really, if you have the good scale, you can really tell what is the exact composition of what you are analyzing. And this is a mass spectrum extracted from a sample of Murchison. So each peak here is an organic compound. If you zoom, so here it's from 200 to 1000. If you zoom from 315 to 324, you see that there are a lot going on. And if here you zoom from 319 to 319.3, you see that each peak is a formula, and here it's the most expanded data you can get. It's a zoom between 319.13 to 319.14, and each peak is a formula of a molecule. And you can get beyond that, because for this exact formula you can have maybe, I don't know, 5, 10, 20 organizations that would lead to this peak. So that's an illustration of the diversity of organic compounds that are present in carbonaceous chondrite. But, well, carbonaceous chondrite, as I said, is, well, a few percent of organic material. The remaining is inorganic. In this organic material, I've focused on the soluble fraction, because, well, that's where you get the fancy, interesting, so-called prebiotic compounds. That's where you will get the nitrogenated bases, that's where you get the amino acids. But it's not the majority of the carbonaceous contents of those meteorites. The majority of the carbonaceous contents of those carbonaceous chondrite is made of what we call insoluble organic matter. So that's actually what is in those chondrites. So here you have the soluble part. And, well, we have a lot of tools in the laboratory to see what this soluble part is made. But when it's something, yes?
Can you give the solvent of the soluble fraction?
Well, that's an excellent question. It depends. What is the solvent of the soluble fraction? Well, you start with water, then you move to methanol, then you make mixture of polar, apolar, and actually in the paper I've discussed just before, they use a series of solvent and solvent mixture. So yes, what you call soluble depends on the solvent. That's a very good remark. And the insoluble, but we have no proper tools to address that. But the insoluble fraction, well, it's been studied for years, since the 70s, and well, we still barely know what it is made of. We know ratios of carbon, nitrogen, oxygen, sulfur, but the actual structure, organic structure, is something that after years and years, people working on that, they don't know exactly what it is. So this is one structure that is proposed by Sylvie de Rennes and François Robert. It was in 2010, but it's not like you have a formula of a molecule. It's an hypothesis based on various analysis, and it's not a structure with a beginning and an end. It's something that is spread out like that, and quite quite difficult to fully understand. You've seen this picture yesterday. So if you take some extract of the organics that are inside carbonaceous chondrite, and if you put them in water, part of the insoluble material will spontaneously make vesicles. So, well, from that it's easy to say, okay, you have the organics, you have the insoluble, you have the soluble, then you have everything you need to make life. No, that's too straightforward. But what is interesting in that is that the meteorites that are falling on Earth right now, well, they have the same composition than the meteorites that were falling on the primitive Earth, and so we have a good model of some of the ingredients that were brought to Earth, and it's not depending on any theory, any modeling, any hypothesis you would have about the composition of the atmosphere, for instance, the redox state of the mantle, well, what we don't know exactly is the amount. If you have had a late heavy bombardment or not, if well, you've heard about the scenarios, the various scenarios of the solar system formation on Monday. So well, it's changed every other year. So that's a big unknown. How much? We know probably what, but how much we don't know. Yes? It will be some. Well, I don't put the scale, but well, it's something you probably be able to see by eyes. So tiny, extremely tiny things. I don't know really if you have the scale.
It's microscopic. You cannot see by eye.
Okay, you cannot see it by eye. Okay, I have never seen them, but it's okay. I've talked about carbonaceous chondrites. These are micrometeorites. So I've already said that the flux is much more intense than meteorites. And recently, a new kind of micrometeorite was found. So there were micrometeorites that were roughly matching the composition of carbonaceous chondrites. But since 2010, there's a new kind of micrometeorites that are called ultra-carbonaceous Antarctic micrometeorites. And in those small objects, more than 50% in mass of the micrometeorites are made of carbon. So it's not the few percent of the carbonaceous chondrites, it's a large fraction. And also there's a large high content in nitrogen, which is not the case in carbonaceous chondrite, which are quite depleted in nitrogen. In those small objects, tiny objects, here you have the scale, you have a lot of nitrogen compared to other exogenous sources you can get from space. So this is what you can actually observe on Earth, analyze on Earth. There is another family of objects orbiting the Sun, comets. So the difference between asteroids and comets is that the comets, when they get close to the Sun, they have some activities. There are a high content in ices, and then when the nucleus gets warmer and warmer, the ices sublimate. And from the 70s, the 60s, 70s, we have a lot of data about the composition of what is ejected from the nucleus. So the gaseous phase, you can analyze the gaseous phase of comets from Earth with infrared telescope, radio telescope. And so here you can see a table with the list of the compounds that have been detected in the gaseous phase in the atmosphere of the comet. So the main component is water. So all the other compounds, their abundance is shown plotted relative to water. If you see sometimes black and light blue, it means that from one comet to another you can have this variation of abundance. So all the comets are not the same. They show variety of composition in terms of gaseous phase, and you will see hydrocarbons, you will see alcohol, aldehyde, nitriles. There's any kind of stable combination of H, C, N, O, and S will be found in the composition of the atmosphere of the comet. That's the gaseous phase, and most of those detections were made remotely from the Earth. But you've heard about it. Recently, the European Space Agency sent a spacecraft called Rosetta, and it was a two-part laboratory. A lander that was meant to land and make some analysis on the nucleus. So it bounced, but then in the end it was able to perform some analysis. I will talk a little bit about that. And on the spacecraft you also had a series of instruments to analyze the comet. And the specificity of this mission is that Rosetta was around the nucleus of the comet during 2 years. So it was not just a flyby, it was really a long-term mission which ended in September 2016. Some of the instruments were meant to analyze the organic composition of the comet. So there are a lot of wonderful pictures. I will skip them. This is the nucleus. Actually, it's extremely dark. It looks like light gray, but if you measure the albedo, the actual albedo, it's like coal dark. It's really dark, which might sound surprising because it's an icy body. But well, there's ice, but the ice is inside, and what is outside, well, it's a mixture of mineral and organic matter. So I can't resist to show you some of the pictures. Here you say here it's dust particles that are ejected from the nucleus. So the gas is sublimating, and it's taking with the gas some dust particles. On Philae, 2 instruments were able to say something about the organic composition. It was too short. It was not operating as it was meant to operate. But for instance, the Cossack instrument was a GCMS, so a gas chromatographer coupled with a mass spectrometer. So the mass spectrometer was automatically switched on when Philae landed at the surface. And here you see a mass spectrum that was measured when Philae was still plugged to Rosetta before landing. So that's the background of the instrument. And here it's what was measured when it was thought to be sitting at the surface, but actually it was bouncing. And the understanding now is that when it bounced, it lifted some dust particles from the surface, and some of them get into the pipes and they sublimate inside the instrument. And you see a lot of peaks at various masses. It's one shot, it's one spectrum. A few days later, 2 days later, before Philae had no more energy to work, it was in a cold place of in the dark of the nucleus surface. You're roughly back to the background. So there's really something going on here. So it's difficult because there was no chromatography before, so you have to address the whole spectrum and make some assumption about what it's made of. And so the one interpretation of this result is that this list, so you can see it better here, this list of compounds were actually sublimating from the dust particles, and they were analyzed by the mass spectrometer. There can be other combination, but that was the one that was published by the team, the instrumental team. And one of the conclusions which is interesting is that this combination match the kind of chemistry that would result from an ice mixture made of water, CO, methane, and ammonia. You have this ice mixture, you put some energy by photons, by energetic particles from the solar wind, cosmic rays, and this kind of chemistry would result into this combination. So it's not only a question of having detected those compounds, but put them into a context. The organic composition of an object can tell you something about its history. But a lot has been going on with Rosetta. Rosetta had instruments that were meant to take pictures, to make physical measurements, but also to measure the composition. So this is a nice view graph that was produced by ESA to somehow summarize the organic compounds that have been detected not at the surface, but by Rosetta, by the Rosina instrument, which is a mass spectrometer dealing with the gaseous component of the cometary atmosphere. And you see this list of compounds. So it's a nightmare for chemists, but it's been designed by physicists. So they're not familiar with the chemical family, so they put molecules like the smelly molecules because they are smelly. The poison are together. So a chemist would put the nitriles with the other nitriles, the aldehyde with the other aldehyde. So that's not how this list has been done. But at least it's funny. And sitting in the middle of the zoo, the claimed king of the zoo is glycine. Why glycine? So glycine is the simplest of the amino acid. So it's somehow iconic because if, as I said, you can say we have amino acids, so we have peptide, proteins, and life, and so on. So there's a lot of attention always that is attracted by such molecules. So it's been granted the title of King of the Zoo, and so this is a detection of glycine. So it's a mass, the exact mass of glycine. You can say yes, but there might have some other combinations of atoms that might result into the same exact mass. That's true, but then if you look in other parts of the spectrum where glycine is detected, you see that the fragmentation pattern is consistent with glycine and not the other isomers. So glycine is detected in the Rosina data, and it shows us unexpected behavior. It shows here you see its distribution as a function of the distance from the nucleus. So if it was normal, I mean emitted from the nucleus by sublimation, it would be a straight line because it's the density here multiplied by the square of the distance. So it should be a straight line if it was only released from the nucleus. The squares are the glycine data. The stars is the total density, so the total density is flat. Glycine is not flat, and it means that there is what we call a distributed source. So glycine is released not only from the nucleus, but also in the atmosphere from the dust particles. And Katia here is struggling with those data to make sense out of it. And it's not hard to get glycine. It's iconic because it's the simplest amino acid, but it's not very difficult to understand, at least in the cometary context, how you can get glycine. So this is a paper published by a French team working in Marseille. It's ice chemistry. So if you freeze CO2 ice with methylamine ice together, you warm it, just rise the temperature. You don't need photons or whatever. You will have spontaneously the formation of this salt, which is called methylammonium methylcarbamate. And then if you add some energy, UVs, you will rearrange this methylammonium methylcarbamate in methylammonium methylglycinate. So it's the salt of glycine. So in 2 steps, with components that are detected in cometary ice, with just heat and photons, you get into glycine. So, well, it's not because you get glycine that you understood the origin of life. That's one of the important message I want you to get. And it's not the first detection of glycine. It's more a confirmation, because in 2004, a space mission from NASA called Stardust flew in the atmosphere of a comet called Wild-1, and it brought back in 2006 samples, tiny dust samples of this comet. And the mineral part the analysis of the mineral part of those dust particles was really okay, but the organic part was very complex because there were already some organic material in the aerogel that was meant to collect the dust particle from the comet. So it's a nightmare to really understand the organic composition of those dust particles. But in 2009, a team from NASA Goddard Space Flight Center published a detection which is really quite convincing based on isotopic ratios, measurement that said that glycine was probably in the sample returned by the Stardust mission, but you could not be 100% sure whether it was glycine already in the cometary dust, or if you had the precursors that would turn readily into glycine when you start to make the analysis. With Rosetta data, it's really, there's no sample preparation, and it's really straightforward in the atmosphere. So it's a confirmation of something that was suspected. How all this stuff got there, and then eventually on Earth. So you've heard already about the Myler-Urey experiment, simulation of the primitive Earth atmosphere in a balloon with liquid water energy. Well, you can have the same kind of ideas and make the same kind of experiment in the lab, but not dealing with the primitive Earth atmosphere, but cometary or interstellar ices. So you know the basic composition, the main components. So then it's not based on assumption. You really take what is the most prominent organics that you observe in comets and interstellar medium. You freeze them on a cryostat, and then you can warm them, you can irradiate them with photons, protons, or whatever you're able to get in your laboratory. So it's simulating the kind of energetic process those ices undergo in the, probably before the comet is formed. Because you don't imagine photons or even energetic particles to go meters, tens or kilometers down inside the nucleus. So it's before the comet is formed on tiny particles. And here you see a picture of what you get when you make your experiment. So you can probe by infrared spectroscopy the evolution of the ice. And well, you switch off your experiment in the evening, you let it warm back to room temperature. And even though you started with methane, water, ammonia, methanol, that would be, it's under vacuum, they would be pumped away when the ice would sublime. Even though you started with that, yes, you get that complex residue, organic residue that stays stuck on your sample holder. These are better pictures that were taken recently at IAS in Orsay in France. So it's like a brownish, yellowish stuff. It depends actually on the dose you put into your residue. Just like when you make caramel, if you have the nice amount of energy, you will have a liquid, light brown caramel. And if you, like me, don't know how to do it properly, you would get something that is sticky, brown, dark, and then you have to trash your your pan because it's well, it's roughly the same thing. Here you see it's a light liquid matter, but if you enhance the energy, you will get something that is, well, you don't want to test that. It's not. It looks. Sorry.
What was this experiment?
So it was something like that. It was a mixture of, it was water. In this lab, usually they use water, methane, methanol. A source of water, a source of carbon, methane and oxygen, methanol, and nitrogen, ammonia.
But this is done in vacuum.
This is done in vacuum. And then you go back to room temperature, you get back to you take it out and you get that. And it's extremely hard to really analyze the composition of this residue, but depending of the initial conditions, the kind of ratios you have in your ice, the kind of energy deposition, but well, you can get to that kind of diversity of organic compounds. So you can explain the diversity of compounds that is observed in comets and carbonaceous meteorites. There are other scenarios, but I cannot get into all of them. But we understand why there is chemical diversity in those objects based on this kind of simulation experiment and others I don't have the time to address. And here you have amino acids. So as always, amino acids get a lot of attention. But you have to keep in mind that in this experiment, for instance, published in Nature in 2002, you detect serine, glycine, alanine, and other amino acids. Here it's more spectacular. It was Munoz-Caro et al. In Nature in the same issue in 2002. You have a lot of compounds, but well, it gets back to the question of the solvent. What you get, how you turn it into a soluble fraction. And the classical way to approach that, both in meteorites and in those lab experiments, is yes, to put them into water, to extract them with water, and then put them in a bath of 6 mol per liter of chlorhydric acid at more than 100 degrees. So it's extremely harsh condition, and you have chemistry going on when you are preparing your sample before you analyze. So the thing is that glycine, you will spot it no matter what you do. The other amino acids, it's more depending on how you prepare your samples. So that's something to keep in mind regarding the fact that you, for instance, you would like to find them in comets in situ or after preparations. So it's not the same thing. So it's when you read that something is detected, well, you need to pay attention to how the sample was prepared, especially with those natural or complex samples. That's an important thing. But well, one could say, and I'm not disagreeing that much, that it's just to enhance the kinetics, and if it fell on the Earth, even though you have the precursors, after a while you could get this molecular complexity just because it sits in water. But it's not that straightforward. And I go back to the chirality question. So that's the slide that I missed at the beginning. So this is the formula, the 3D formula. The bolt means it's behind you. The dotted line means it's bolt is in front of you. Dotted line means it's behind you. And so those two enantiomers are two configurations of the same compound, but they're not actually the same. And still working with ice irradiation, a team showed that if you start with a mixture of water, methanol, ammonia, and simple compound like that, and you do the photolysis not with a standard UV lamp, but with a UV light that has been polarized light in one direction on another direction, you would get an excess of one of the enantiomers compared to another. Either it's not clear, it's at the it's within the synthetic process, or once it's synthesized, the UV light will destroy more one compared to the other, which means that in the end you have an excess of one to the other. So there is some kind of understanding not only of the molecular diversity that is found in the small bodies, but also of the enantiomeric excess. So that's a good model, and you can explain that you have such specific UV light in the interstellar medium. It's been observed already, so it makes sense. Okay. So if you followed well, you say, okay, we're done with the small bodies, but I could not resist to highlight more Rosetta results, because I've discussed the gaseous phase, but I've been working more on the solid phase. And so one of the instruments of the Rosetta spacecraft was called COSIMA. It was relatively a big instrument. It was 20 kilograms. And this instrument was meant to collect dust particles that would be lifted from the nucleus, and randomly they would be collected by the instrument. And then we can perform also a mass spectroscopy analysis, like Rosina, but not with the gaseous, but directly on the solid phase. So it's an amazing instrument because it's like a toolbox. So you have here a target store when you can take a series of 3 small sample holders, 1 by 1 centimeter, and you put them outside. At the outside of the instrument, at the outside of the Rosetta spacecraft. So you could get some dust particles that get there. Then, well, we can decide, take a picture. There's a microscope, and we can take a picture to know whether we get something or not. And if we get something, we can decide to go to the analytical part of the instrument, which is a TOF SIMS, time of flight secondary ion mass spectrometer. So there's an ion beam, and you target a part of your sample holder where you know, because of the picture, you have a dust particles, and it would create secondary ions that are a component of the surface of the sample you are analyzing, and then you measure the mass of the fragments. So it worked extremely well because here you see it's a picture of so 1 by 1 sample holder on May 11, 2015. You have small dots that we know are already dust particles that came before, but that day we decided to put it to the collect position, and the day right after we took another picture, and this is what you see. So the surface of this sample holder, it's 1 by 1, is covered by tiny dust particles coming from the nucleus, and basically it's small parts of the dust nucleus that were collected at low velocity, a few meters per second, up to 10 meters per second. So you see they crush gently, but their molecular composition is not affected. It's just like you walk and you take a wall because you're looking at your smartphone. So it will hurt, but your molecular integrity is not changed. So that's how it's been collected. And it took us a while to really understand what it was made of. I will explain you why. So here are two particles. So we gave them names, first names. So this is Kinef, this is Juliette. We all had in the team a particle because first we named them after us, and then we had too many particles, and we named them after any first name we could imagine from any language of the people of the team. So we have a large library of names. And the mineral part was quite easy to see, but the organic part was not that easy. And Anaïs Bardin, she was there a few years ago. She was a PhD student of mine. At some point, she realized that she started. We show those because that's a history of the understanding. She said there's something going on those particles because the carbon is really the signal of carbon is really rising when we get on the particle, because we were not analyzing just the particle, we are doing line matrices to see the environment of the particle and the particle itself. And you see the signal of carbon is rising, but it was not. We would not understand. You see here in black, it's, well, the signal we measure next to the particle. So it's the background. And it's very important because, well, anywhere you go, when you build an instrument to do an organic analysis somewhere in your lab, but it's more important if you go to space, you bring your own organics with you, always. We call it contamination, background. Actually, sometimes it's quite useful because you do your calibrations, because you know your contaminants, and you use it to calibrate your instrument. But you bring your organic with you, always. So the important thing is to be able to distinguish what is your instrument, and in this case, what is the comet. So black is the instrument. Red is the comet. And you see a signal, clear signal of sodium, silicon, iron. What is good with iron, you see the black, there's no iron at all, so there's no contamination. So 100% of the iron comes from the dust particle. So we are sure we are really on the dust particle, and when we are doing this analysis. And for the carbons, well, we don't see much. We see a clear signal at the small messes, at 12, 13, 14, 15. Compared to the background, it's also quite convincing. The black is really low compared to what we see at the comet. And, well, that's not what we were prepared to. For 10 years, I've had students, I've done some of them myself. We built a library of organic spectra of molecules that we thought we might find at the comet. So hydrocarbons, nucleobases, polycyclic aromatic hydrocarbons, well, any kind. Well, we built this large library, and we had nice spectra with peaks, and from the peaks you can go back to the structure. So we were expecting to see something that mixed, that complicated, that we would barely be able to understand what was there because we had too much of carbon signal in the comet. So here you see the pattern of CH X, H, Y. Sometimes you see the main peak of the at the molecular mass of the molecule. We are expecting to have a lot, and we see none of them. We see only 12, 13, 14, 15, and a little bit at 20, and a little bit less above, but barely nothing. So it's not what we found. And finally, in our library, we found that we had some material, the insoluble organic matter I've talked about before, extracted from the Murchison meteorite, and it was the best match we had. So this complex organic network, when you analyze it with our instrument, you can go on NIST or internet and use a database. This ionization mode, you really need to do your own database. And we had analyzed insoluble organic matter. First, we thought it was not working, so it was discarded, and then Anaïs figured out that it was actually roughly the same behavior. So it's macromolecular. You would expect to see fragments at high masses, but you only see fragments as small masses at 12, 13, 14, 15. Not exactly the same for this analysis, but it was the only way to really match our data. So this is a better view, but I will go faster. So this is on particle, off particle, and various insoluble organic matter would meet the same requirements and match our observation. So what could it be? Yes, it could be insoluble organic matter that I showed, but we've made some new measurements, and Robin worked on it. We've analyzed kerogens. Kerogen is also kind of complex, messy organic material you find on Earth, which is the remnants of biotic organic material that has been buried, processed, heated, compressed, and that's what you get, the kind of stuff you get in the end, and it has the same kind of signature with Cosima instrument. Our calls also behave the same. So I found recently things that show better, I think, the complexity of the material we see. This is this kind of view. This is not insoluble organic matter, but it is kerogen, and people published recently a 3D view of what the kerogen is made of, and it gives a good idea of probably what the dust particles are made of. So it's not something flat, something you can really write the formula and give a name. There's really no beginning and no end at the structure. It's that kind of carbonaceous matter we observe. So important question is how much? So here is a picture of Anaïs. Donia also, we worked a lot on the interpretation with Nicolas, colleagues of mine at LISA. We worked a lot about the quantification. First step was what? Next step was how much? And to make a long story short, our conclusion is that in the dust particles, we have roughly 30% of carbon, 30% of oxygen, 30% of hydrogen. Hydrogen is an assumption. The other one are measurements. And Robin is working on not doing hydrogen an assumption, and is actually quantifying the hydrogen. So this is in atom number. This is the same, but in atom mass. Yes, hydrogen is light, so it's not a lot of the mass. And with some, let's say, educated assumption to part the atoms, the elements between the organic and the mineral part, we get to the conclusion that the dust particles are made of roughly half of mineral and half of organic. So if you want to get a broader view of what the comet is made of, you have those molecules that are detected in the gaseous phase. The question would be, of course, to quantify them. It's not easy, but we have good quantification for other comets. In comet 67P, the comet of Rosetta, we don't know exactly yet the quantification, but it would result in a few percent of the gas compared to water. And then the next question would be to match and to put together the volatile back to the nucleus and the dust back to the nucleus. And there's still a big unknown in the data, which is quite disputed right now. It's the dust to ice ratio in the nucleus. So you will learn that, but the winner is the one who published first, or at least the one who published. And so I know people, a lot of people are discussing that, don't agree, some don't agree, but the first publication that really addressed that has been accepted, gets to a dust to ice ratio of about 7, which is extremely high. In the post-Halley area, the rough ID would be roughly 1. Dust to ice would be 1. But, well, it's one comet, it's one publication. It will take probably a few months or a year before you have a better ID. But I take this number, 7. So what does it mean? It means that the carbon budget in the comet would be roughly 7% of the carbon would be in CO2 ices. 2% of the carbon would be in the zoo. So I took Pokemons and not animals to represent that. And, well, 90% of the carbon at the comet would be in this form of this complex macromolecular network. And Nicolas Frey had this idea to put a well to say that it's macromolecular, but a well is a well has a name, a well has a beginning and an end, and we've really addressing here materials that are much more complex than we previously thought. And maybe there are still things we haven't yet discovered, but even though we have not seen them, it's probably in the form also of large structures and not amino acids, nitrogenous bases. At least at the detection limit we have there, it's not there. And then if you mix the mineral and the organics, you get to this idea of a nucleus that is made half of mineral and half of carbon. That's the conclusion we have at this stage, but it's an ongoing process, and it will take years to extract all the information we had from the data of Rosetta. Okay, so now we are done with the small bodies, and we have, 10 minutes left. Yes?
A question. Seeing that in the stuff you showed, there's a lot of aromatic rings, and why aren't there any sugars? You have the oxygen, you have the hydrogen, you have the carbon.
Yes, so I think it's a matter of cooking. There are experiments, ice irradiation, that turns to at some stage, and they see sugars. So ice irradiation can result into sugars. So maybe it's below our detection limit. I cannot say it's not there. But if you push the dose at a higher total dose, then you will turn your sugar molecule into nasty, dark residue. And my feeling right now is that what we see at the comet is something that are not the volatile part, but what is solid is something that has a history of radiation or heat that processed probably in this comet much more than the traditional lab experiment we're doing. Just because I have 10 minutes, And but okay. So I said I will make editorial cuts. It's frustrating, but I will skip Mars. But you will have 1 hour and a half on Mars tomorrow. I was planning to say a lot of interesting stuff, but I won't. But I can't resist just to say, yes, if you have an instrument and if you want to see something, and usually in science you are at the limit of what you're able to see. Otherwise, someone has done the job before. So if you are too biased by what you want to see, you will. Here is an example. This is a famous face of Mars. Probably none of the people working on the instrument believed at that time it was a face, because they knew the limits, the limitation of the instrument. But, well, you tune a little bit your contrast and you see something, and it was for some proof of life on Mars. And then later on, you have better instruments and you can rule out this hypothesis. So you have really to be conscious of the limits of your instrument, and you have to know how it works. You cannot just okay, I push the button, have the result, and take it for granted. That's important. So I have to skip that, and I go and I will finish on the icy moons. Icy moons are somehow the new El Dorado of the solar system exploration. Why? Because some of them are quite interesting. Here you see Europa. The surface is made of ice, but the way Europa turns around Jupiter, the way Europa turns on itself, modeling of its internal structures, results in the idea that below an icy crust, you would have liquid water and then rocks. For larger icy satellites, it's just thermodynamics and the phase diagram of water under ice pressure, but you would have ice, liquid water, and ice. On such objects, so you don't, if you ask the question how you get organic matter, well, you don't have an atmosphere, so you cannot address the synthesis in the atmosphere like it's possible on Earth. You can have comets, meteorites crashing at the surface, but you have no atmosphere to slow down, so it's quite the impact is quite hard, and you have to imagine ways to get the materials that survived at the surface inside. There are mixtures, there are ways, but it's not straightforward. Then one thing is left is for Europa and also on Enceladus around Saturn is the fact that in the icy moons where you have the ocean in direct contact with the rocky crust, you can imagine that you have geothermal activity, and then the water getting into the rocks, it's heated, it reacts with the minerals, and on this environment you have, at least on Earth, you have a mixture of organics that are quite reactive, and in those environments, when you simulate them in the laboratory, you get organic synthesis. You would get amino acids, for instance, that are synthesized. So you have organic synthesis, and well, you cannot exclude that you have hydrothermal vents on those inside those icy moons, the one with the liquid in contact with the rocky crust. So that would be okay for Europa. Ganymede, Callisto, it's to the current state of our knowledge, it's not really possible, and so there is a lot of activities right now are about going back to those icy moons, make sure there is a liquid ocean. Well, some would say it's 99.99% chances there is actually liquid, but we have not proved 100%. And so land and maybe go inside and see what is there. And I showed you at the beginning that there is a lot of interest and a lot of press, at least, saying, yes, we have energy, we have liquid water, we have organic, so we have life, but we are not sure about that. Enceladus is smaller than Europa, but roughly it's the same case: ice, liquid water, and then the crust. What is interesting for Enceladus is that you not necessarily have to dig because you have geysers that are ejecting material. So if you could have access of material coming from the internal oceans from just flying above Enceladus. Titan is another case. It's also an icy satellite, and you don't see the surface. At least when you look at it in the visible, you see the surface is hidden by a yellow haze, and this yellow haze actually is made of organic matter. The atmosphere of Titan is made of nitrogen with a few percent of methane. And if you do that kind of mixture in the laboratory, if you put energy, electrons, photons, protons, you would synthesize a messy organic residue. In the laboratory, we call it tholins, which are a solid component, extremely complex also to understand its actual composition. So it's an organic chemistry lab at the scale of the moon. So if the primitive Earth had a sufficient amount of methane in its primitive atmosphere, you can imagine that on the primitive Earth, the same kind of organic chemistry could have occurred, plus liquid water at the surface, which is not the case on Titan, because on Titan you would be in the case of ice, liquid, ice, and then the crust. Okay, back to the recipe, and it will be somehow the conclusion. So we talked about carbon, water, energy. So does it really make sense to be that focused about water? Well, the answer for me is quite simple and would be yes. First, because water is extremely abundant in the universe. It would be the second most abundant molecule after hydrogen. So there's a lot of water everywhere. Liquid water is another question. Liquid water, there's on Earth, for sure. Probably on Mars in the past. Probably below the surface of icy satellites. Probably on exoplanets, but for sure on Earth. It's for the remaining, it's yet to be proven. Water has physicochemical properties that are very specific. You cannot find the same combination of sustainability in the liquid form on a large range of temperature. Its capacity of putting and matching molecules together, that's a specificity of water. Some chemists working on water would call it a molecular matchmaker. I said it has not been observed yet in the liquid phase beyond Earth, but, it's a solvent. And nobody has ever proven that liquid water means necessarily life. And it's could be the best and the worst for life. Because, okay, it's good to have water to make some reactions, but some important reactions that are needed for life, like the combination of amino acids to make peptides, they, like alanine and glycine, if you want to combine them, it's a reaction that frees one molecule of water. It's an equilibrium. So if this occurs in water, the equilibrium will be way to the left. So you need to find tricks. It's possible, but you need to find tricks to get around this. And some of these tricks, basically, so this is a kind of complex scheme to polymerize peptides. It requires a dry phase. Some occurs in liquid water, but you would not be able to link the amino acids if at some stage you don't have a dry phase. More recently, last summer, there was a paper talking about the origin of the RNA world, and it was called The Fate of Nucleobases in Warm Little Ponds, a direct reference to the idea of Charles Darwin. And again, to build those structures together, there was a need of a dry sequence. So it questions the fact that if you are in a 100% ocean liquid phase in the icy moons, you would be able to have this dry phase. That's not straightforward. So even though you have liquid water, organic matter in the icy moons, if to start life can evolve and get adapted to 100% liquid environment, that's not a problem. But to start life, you need at some point a dry phase. Well, thinking it's possible in a 100% liquid ocean, it's to be questioned. The carbon. So carbon chemistry, it's universal. You observe in the interstellar medium a lot of molecular diversity. I've discussed extensively what is the content of the small body. So diversity, it's not questionable. The carbon can get to a lot of components. The term complex is quite difficult because the messy, insoluble organic matter, it's complex if you look at it as a chemist and you want to understand what it's made of. But in terms of organization, well, it's nothing but organized. It's really carbon linked to other carbons with other atoms. There's no organization. So how you get from this complex and quite abundant, as I said, insoluble macromolecular material to things that is useful for the start of life, it's unknown. But like water, it seems that there is a bias of organic chemistry towards life, and now even recent organic chemistry books they can't reference to put, a butterfly, a tree, a flower on the cover, and I think it reinforces the idea that organic chemistry and life, like in the 18th, 19th century, are connected. But no, the chemistry of carbon is chemistry of carbon, and nothing proves that complex chemistry of carbon will result into life. So I better like this cover because it's really hardcore organic chemistry and no dream or fantasy on the cover. But maybe they get better sales with cover like that. And as I said, the reactive components, either in the meteorites or comets, the fancy, funny, interesting compounds that you can play around with to react and get interesting things for the origin of life, they're only a tiny fraction of the carbon that is brought to Earth from space. Most of it, either in meteorites or in comets, is in the form of a complex molecular structure. So maybe we don't need that. We need the tiny fraction. A few ppm is enough to start life, but most of the carbon that has been brought to Earth, we have to keep that in mind, has been brought to Earth in this kind of macromolecular form that is not really reactive. It's like it's like coal. You know, you don't start an organic synthesis with a piece of coal, but that was available on primitive Earth. And if you make some summary of what occurs if you do simulation of the Earth atmosphere, Stanley Miller got famous for the amino acids, but it was a small amount, most of what is synthesized when you do the Miller experiment is that kind of dark brownish stuff that gets into the water, but most of it is insoluble. It's what remains most of the time when you irradiate ice mixture. And here it's an experiment that was, this is Clifford Matthews. He worked on basically his whole career on HCN. HCN is very reactive molecule, but if you let HCN react by itself, it will form yellowish polymers and then a dark polymer, and then you have a dark powder from which you don't get much in the end. So we have this idea about the complexification like a linear process, but well, most of the carbon is available under this form. So when we look for carbon on Mars, if we look for carbon on Mars, not necessarily to find life, but at least you have the meteorite, comet that brought organics at the surface. Most of the instruments, they are tailored to detect, yes, the amino acids, the small compounds, and well, but if there is organic on Mars coming from outside, it's mostly under this form. But it's very hard. Even in the laboratory, we don't really know how to address that. One example for linear complexification is the chemistry of hydrogen cyanide. You put 5 of them. It's pretty easy on the slide, and you get adenine. Another way to make it. This is HCN polymer, a work from Matthews and Minard. So, and they worked on HCN, then they work on HCN polymers, and they have some scenarios from these long HCN polymer chains. In liquid water, you can extract part of it and get the adenine from this macromolecular stuff. So maybe there's some kind of bypass somewhere we have to take into account. So here's adenine. So maybe the prebiotic source was the source of macromolecule. That's a question to take into account. Last word about the energy. Is any kind of energy okay? What do we have in the oceans of the icy moons? Okay, we have the icy layer, we have liquid water, and let's say it's okay, we have hydrothermal activity. So you have the triptych, energy, liquid water, organic compounds, but remember that. If you want to start this autocatalytic replicative process, I told you it comes with an energetic cost at the beginning. And colleagues like Robert Pascal, Adi Pross, John Sutherland worked a lot on this concept in both in the kinetic and thermodynamic point of view. And their conclusion, it's consistent, maybe they miss some point, but in their view, the theory, which is quite convincing and consistent, this energetic cost, you have to put it at a level which is met by visible and UV light or lightnings. You won't get that kind of energy in hydrothermal vents by thermal process or even by redox processes. So, ingredients for life. So you have everything in the icy moons. So you have those schemes, you have liquid water, you have the, the beasts that are going at the surface, and you will find their remnants at the surface. I don't say we need to go there. We need to make it's fantastic. We really have to address this question, but it's not obvious. For instance, John Sutherland, one of the best chemists, I think, at this currently, wrote a requirement for ultraviolet irradiation to generate hydrated electrons would rule out deep sea environment. This, along with a strong bioenergetic and structural argument, suggests that the idea that life originated at vents should, like the vents themselves, remain in the deep bottom of the ocean buried. So, that said, so it's written, he rules entirely out the idea that life could arise in those oceans. Or if it worked, somehow it might be entirely different than the life that could arise on Earth with access to dry environment, with access to light, UV light, lightnings. So that's something to keep in mind. So, conclusions. Understanding the prebiotic chemistry, another quote by John Sutherland. I suggest you read his paper from last year. It's called Studies on the Origin of Life, the End of the Beginning. He says we are not yet close to achieving this end, understanding the prebiotic chemistry. We are not done yet. But he's optimistic. He says that we are finished the first phase, the beginning. At least have a good understanding of and good conceptual ideas of how it worked and get started. We are also in a wonderful time where we can really address the possibility of life beyond Earth in the solar system. Frank will talk after me about beyond. I didn't talk at all about the exoplanet, but in the solar system we have wonderful tools. We have MSL, Curiosity, currently working on Mars. We will have ExoMars soon that will be able to dig, to work beyond what has been done. We have this icy environment that we need to go there, at least at the surface, maybe later in the depth of those oceans. But a key question is to have the right instruments, because if you are in your laboratory, you have a new sample, usually you change your instrument or you go next door, because usually what you already have, when you change your samples, it's not okay. Now we are building instruments for completely new environments and the surprise of very oxidative rocks at the surface of Mars that would react during the analysis that made things extremely complicated for Curiosity. So we need to think about instruments that can be quite versatile and get adapted to unknown environment. And the best way is to have a sample return. So, last word, we will be able to say we understand the theory of life when we are able to find at least another form of life somewhere. Until then, we are speculating, educated speculation, but we are speculating. And last word is that we have to keep our feet on the ground, on Earth, on Mars, and even in the oceans of the icy moons. So, thank you very much.